Hello and welcome to Team AF's booth for Capstone Day 2021. The year 2020 shed light on various unique challenges faced by healthcare systems all around the world. The shortage of intensive care units was a widely discussed subject at the start of the year. Upon inquiring into the matter further by speaking with several medical professionals from Gujarat, India in September, we identified that there was a lack of trained medical professionals available to care for patients experiencing breathing problems, especially hypoxia. Regardless of the factors causing the hypoxia, patients would need immediate access to ventilators. In such situations, manual ventilation would need to be administered during journeys to closest ICUs with available beds, which could take a substantial amount of time. With limited help available due to the stress on the healthcare system caused by the pandemic, often a single medical personnel is split between manually pumping a back valve mask to ventilate the patient and several other care tasks. We identified the need for a lightweight, unintrusive, sustainable, and compact automation solution to the manual pumping of the BVM. We designed AutoMate, a pneumatic-driven solution, to tackle this distinct local challenge, but believe that our solution could be scaled for global use after minor modifications to the design based on regional requirements. Without further ado, let's look at the working model of our system as is. We have designed a pneumatic solution that would use the air compressor on board an ambulance. This air compressor will be used to supply pressurized air to the rest of our pneumatic system. The pressure right now is set to 80 psi, and its supply can be turned on or off using the manual on-off switch on the air preparation unit. Next is the regulator. The knob on top can be turned to allow a maximum of air pressure of up to 80 psi currently, and can be locked into place once you are satisfied with the pressure setting. Next is the auto drain. This is going to be the component that drains out any excessive dust or moisture in the system. There's also a silencer mounted on the manual on-off. There's a barcode on every device, on every pneumatic component of our device that can be scanned using a normal camera. And once scanned, it will show you or direct you to Festo's website, our manufacturer. The air preparation unit is connected to a solenoid valve. It has 5 valves on board. The first valve receives the input pressurized air. The fourth and the second valve in turn connect to a pneumatic cylinder. The valve needs to be powered by supplying 24 volts to it via the power supply, and the LED goes on and off based on power being supplied or not. Valves 5 and 3 are mounted on by silencers to ensure that our system is not too noisy and bothering the patient. There's also a small screw on top which can be pressed to just manually check if the cylinder is working or not in order to troubleshoot any problems with the piston. Valves 2 and 4 connect to the pneumatic cylinder. Valve 2 is connected to the front of the cylinder, whereas valve 4 is connected to the back end of the cylinder. Air being released from valve 2 ensures that the piston is retracted, and air being released from valve 4 will make sure that the piston is extended. The retraction and extension of the piston is controlled by the power supplied to our solenoid valve. If a 24 volts is supplied to the solenoid, our system will trigger an air release from valve 4, triggering an extension of the piston, whereas if 0 volts is applied, our system will trigger a retraction. There are 2 proximity sensors mounted atop the cylinder, one at the front and one at the back. The front sensor's LEDs light up when the piston is extended, whereas the back sensor's LEDs light up when the piston is retracted. Currently, the BVM is being pumped at the rate of 14 breaths per minute which is the desired pump rate. The video demonstration currently is sped up 1.75x times, showing how the BVM is being pumped 14 times in 1 minute. This pump rate can be adjusted very easily by changing certain parameters in the code. Next, we're going to look at the relationship between the piston extending and retracting, aka the pumping mechanism working, and the PLC. We've connected the solenoid and sensors to a circuit as can be seen in the video currently. Our PLC consists of a Raspberry Pi mounted on top by a relay. The third channel of the relay is connected to the solenoid and powers it with 24 volts. The power switches periodically between 0 and 24 volts, triggering an extension and retraction of the piston. The fluctuations in the voltage every time the switch happens can be seen on the power supply right here, and the LED of the solenoid also lights on and off accordingly. Next, let's look at the impact of the output delivered by the sensors to our PLC. We're currently trying to measure the output provided by the sensor at the back. Every time the piston is extended, the back sensor should not have any LEDs on it light up and supply 0 volts. Whereas when the piston is retracted, we should see a reading of 3.1 or 3 volts on the multimeter. This is a miniature version of what our final design will look like. Here, you can see an arm that will be mounted on one of the ambulance walls, the one which is closest to where the patient's bed is usually positioned. This arm will be of extendable and variable length, made out of metal that is able to bear a lot of load and force, because the cylinder will be mounted on the C structure, which in turn connects to the arm. The arm will be of extendable length, but would extend up to 3 feet inside of the ambulance. It will have the C structure over it, which itself would be about 1.5 to 2 feet long. As you can see here, there is a clamp that can hold the cylinder in place over here. The head of the cylinder with the piston will be locked into this holder, and the back side of the cylinder will be fastened over here. This C shape right here, or the C bracket, is going to be holding our BVM in place whenever a patient requires care. The structure, and it is a bit flimsy for now, but the BVM can be put into place right here whenever a patient has come in requiring care. The BVM could already be attached to the patient by the doctors of the medical facility that they are being transported from. Once the BVM is fastened in place, the arm over here can be brought down and clamped right in the pinhole that I was showing previously over here. Whenever the BVM needs to be removed, be it due to any technical difficulties or for whatever other reason, this arm can very easily be moved right back into place and clipped in over here, ensuring that it's not going to move around while in travel and injure the patient. There will be a permanent screw drilled in over here so that the arm is always in place. The BVM can very easily be removed and added back as necessary. This arm can retract after it is not being used all the way back to the face of the ambulance wall again. Here's just a little bit of a closer look to the different pins that will be holding the C structure in place. Another part of our future work, which requires a lot of metalworking, will involve creating a concave plate that will be fastened right here on the piston head to pump the BVM. so that our force and pressure is evenly distributed and there is more load on top of the piston, making it move a little slower than it does presently. This is what we envision our final design to look like, where we've added a few shots of the 3D design of what it would look like inside an ambulance setup right now. Thank you so much for watching. We hope to take this project forward and create an impactful design for the future.
My name is Siddharth. I will be presenting the System Health Reporting application built for this project. In my presentation, I will cover what is the solution providing and why, what is it, how does it work, conduct a short technical demonstration, and touch upon the product evolution strategy and a conclusion. At the moment, there is no automated reporting of device failures in ambulances operating in Gujarat, India. Thus, there is a need for this automated failure reporting for mobile devices, such as an automated bag valve mask or BVM unit. Thus, the implementation of this solution will provide a mechanism to report issues, provide a low-cost mesh-based communication, which will allow other ambulance to support crews that may have fault, provide a way to visualize data as gathered real-time, provide a way to push notifications to users if an issue is detected, provide a way to configure the application during runtime without stopping it, and provide a way to read health data from any type of pumping mechanism using a gyroscope sensor. So in short, what this application is a solution that performs real-time analytics on the health of microcontroller systems in ambulances. It looks something like this, where you have the microcontrollers sending data about their health through the mesh network to a base station PC, where the base station PC processes the data and then sends the data through the cloud into a structured database, where using analytics technologies, that data is visualized and then presented onto a website, a standalone website publicly available to base station personnel and ambulance crews. The base station PC looks something like this, where an XP device is connected to the PC to receive data that's being sent by the microcontroller. And the microcontroller looks something like this, where I have a Raspberry Pi connected to an XP to send data about its health, and then a gyroscope sensor to read data from, which would determine what system health data to send, which would be an error or an OK. This gyroscope data looks something like this. Based on the XY rotation and the acceleration, I would then send data from the microcontroller about its health through the XP. With that, I have my base station on the right here, which is listening for data, and I have my microcontroller, which is sending data about its health. And then you will see that as the data is received by the base station, it is then put into the database. And as it's put into the database, a base station personnel can log into the website to get data about the ambulance, which is in this case ambulance A, and find the updated visual showing the data about the operation of the medical device inside of the ambulance. This solution, as built and as designed for this project, can be deployed into a production environment inside of an ambulance with a functional BVM. The addition of these features here would make this more of a full-up system. In conclusion, this system health reporting application has the potential to improve patient mortality through quicker detection of failure and quicker recovery from failure. If not implemented, it would require someone to constantly report on system health. It is also less expensive than a fully redundant pneumatic pumping mechanism and parts can be found easily. For more information, please visit the website here for more detailed documentation about this product.